We have reached. So hi and welcome everybody to the 1W-Minds talk. So it's our pleasure today to have Anna Veselovska from the Technical University of Munich give a talk about digital half-toning via weighted sigma delta modulation. And Anna did her PhD at the National Academy of Science of Ukraine with Anatoly Holub. She then was a postdoc at the TU Braunschweig and the University of Lübeck. And she is currently a postdoc in the group of Felix Kramer at the Technical University of Munich. So thank you, Anna, very much for giving this talk. And the floor is yours.
Thank you very much for such a kind introduction, and many thanks for having me here. As mentioned today, I would like to talk about digital half-toning and weighted sigma delta modulation or quantization. So both terms, they can be used interchangeably. And this is a common work with joint work with my postdoctoral advisor or mentor, I would say, Felix Kramer. So let me start now with some motivation. Why digital half-toning or later digital half-toning? We have the following. So problem of half-toning raised when we had this appearance of printing industry, and when people realized that in real world images, for example, we have continuous grayscale like here, but when printing we can use only black dots, and somehow to resolve this discrepancy between continuous world of colors and the one that we can print, the idea was to use or to exploit the smoothing operation, which is built in our visual perception. And what do I mean by this? If you would look at these two things from a distance, sufficiently far away, then your eye would not distinguish between the structure of black dots and this grayscale, which is continuous. That's why the idea is that we wouldn't like to have two pictures, the one that is printed and the original one, to be approximately the same, but we would like only that the smooth representation of a figure or a picture is approximately equal to the smooth version of image. And this is because of this smoothing operation that is built in our eyes. Okay, and now we have two types of half-toning. The first one is called analog half-toning, and the second one is called digital half-toning. So in analog half-toning, the idea is that you represent continuous grayscale by black dots. They may be also of different size, for example, like here. And you can place them in a continuous domain. So mathematically, we can say that we have some train of Dirac deltas, which we need to place somewhere around to approximate the image. And this type of half-toning is very well understood in terms of mathematics. So here you can see names of different researchers that were doing a lot of work in this direction. Of course, this list is far away from being complete. But at least you can see some of them, right? And when we go to digital half-toning, we have the dots that are replaced now by pixels, and we have no freedom of having continuous domain. We are restricted to this pixel grid that is strictly discrete. And here there is a wide variety of methods available, and most of these methods, they are coming from engineering literature. So there are a lot of methods around, but not so much mathematical theory. Okay. And for example, one of very common strategies for digital halftoning is the class of halftoning methods that is called error diffusion. And error diffusion has the following idea. So the idea is that you keep track of a certain accumulation error when you halftone pixels, which means when you decide whether the pixel should be black or white, okay? And the neighbors, they pay for, or the pixel on which you halftone should compensate for the error that is made by its neighbors. And here I will show you one example, and probably it will be more clear what I mean. So one of the most famous error diffusion schemes was proposed by Floyd and Steinberg. And in this case, the idea is that you have a continuous grayscale image, so which you can rescale from -1 to 1, and you would like to replace each of the pixels by black or white, or we can say the white is -1 and black is 1, okay? And this scheme tells you the following, so that you can halftone one picture proceeding in the following way. So here is the picture, and I will explain you how to do this here. And you will see many of such pictures in this talk. So that's why let me explain what I mean by this. And next time when you see such a picture, you say, oh, I know what she means. So probably you see that there are darker dots and darker green dots and just green dots. And each dot here represents one pixel. So we go here line by line, and the darker green dots, they mean that you already halftoned this pixel. So which means you have already decided whether it should be set to black or white, okay? And this blue point here means that this is your current position. You are about to halftone this pixel. So you are about to decide, should it be black or white? And this Steinberg-Floyd scheme or Floyd-Steinberg scheme tells you the following. You need to compute the error that is made in this for these four neighbors. So you have the original image and you have the values that you've got from halftoning. You simply subtract the true value from the one that you halftoned and you have some error. And this method tells you that you need to multiply the errors made on these pixels with the corresponding weights. You need to sum them together and to add them to the value of this pixel that you are standing in. And then you decide, is it black or white? By simply taking a sign. You say -1 is for white and 1 is for black. And you are going in this direction of the blue error, okay? So here is one example. You can see here is the grayscale image, and here is the halftoned representation of it, which is done by Floyd-Steinberg scheme. It also depends how the resolution of your screen is. Sometimes you can see more artifacts, or sometimes you can see less. But if you zoom in, then you can see what is going on. That's why if this picture has some artifacts on your screen, or it maybe not have, then you know that there are different, I would say, representations of this image because of halftoning, okay? Good. And the goal of this talk is to study such class of error diffusion schemes, one of examples you just saw, from the perspective of 1-bit sigma delta quantization, okay? So why 1-bit sigma delta quantization? In 1D, for 1-bit sigma delta quantization, there is a very nice theory and understanding how it is going on. That's why we would like to study such schemes and have some rigorous theory for digital halftoning that was not present before. And we need to fix some signal model, okay? So we say, okay, we remember that our eyes, they have the smoothing operation that is built in, or we can mathematically represent the smoothing operation by low pass filtering, okay? So that's why we say that images the true images, they might not be band limited, but how we perceive them, they are band limited signals. And that's why we fix the following model. So we say that we have a set of band limited functions with bounded amplitude, because we say for the range of images we have bounded amplitude, and this is the I would say the mathematical model that we use for our 2D images. So we have band limited functions in 2D with bounded amplitude. Okay, and of course, if we talk about band limited functions, they are beautiful because they are uniquely determined by its samples, by their samples due to the Shannon sampling theorem. Okay, so we say that every band limited function that is sitting in this set here, if we have some oversampling rate lambda, which is bigger than this band with omega, and we have some low pass kernel that is appropriately good for this function, then we can write down this function as simply the weighted sum of shifts of this kernel phi multiplied by the samples. Okay, so which means if lambda is big enough, then these samples, they uniquely represent the function. Good, and having this, we fix some values or some samples of the function f, and for convenience we say we denote the sequence of samples by this y. Okay, so y is now the sequence of samples, and which means that yn is just simply equal to fn over lambda. Good. And I told you that we would like to have this perspective from quantization angle. Then what do we mean by quantization? So quantization was very popular for band limited signals in 1D for audio recording. And usually in quantization setting, you have some quantization map and an alphabet. And since we are in 1-bit setting, we say that we have alphabet that consists only of 2 elements, in this case from -1 and 1. And this sample or this sequence of samples should be now mapped by this quantization map to 1-bit samples, which means we just apply element-wise to each y, and we apply this map q 1-bit. Okay, and in this case we replace the samples here that are just some real numbers by only plus and minus 1. And for now, let's assume that we know how this q looks like. Of course, there are different ways to define such a quantization map, and there are each of them has different advantages, I would say. And now, motivated by Shannon sampling theorem, we would like to find a q, this 1-bit samples of our function. And we would like to find them in the following way, that if we take this original function, then this function is well approximated by its 1-bit quantized representative. And this quantized representative is denoted by fq. So how is it built? It has the same structure as from Shannon sampling theorem, but you replace the samples, the true samples, by the 1-bit samples, okay? So you simply replace the yn by qn here. And of course, you would like to find this q, the one sequence of 1-bit samples, such that this fq is very close to f. And to measure the closeness between these two functions, we will use the following errors. So we consider the error signal EQ, and EQ is defined again using this Shannon sampling idea. So we simply subtract the true samples fn or yn from the qn, and we measure the infinity error of this error signal. And we would like that this infinity error is small. Okay, now, as I told to you, let's assume that we have Q. But if we don't have, the question is how to define this Q such that the error signal is small. And here, what we can do for 2D, there was no such schemes. So, but there is a very rich theory for 1D. That's why we can look first at the 1D case for inspiration. And in 1D case, you again have this quantization map that is doing the same business, but in this case, your sequence of samples is simply 1D. Okay, so this is just some 1D sequence, and then you replace this 1D sequence by Q, which again is the 1-bit sequence, but in 1D. And for band-limited functions, a very efficient method for quantization is the so-called sigma-delta quantization scheme. And the idea of this sigma-delta quantization is as follows. So you say that you would like to find this Q, and you would like, during building this Q, control the accumulated error. And this accumulated error is controlled using some new sequence, which you defined every time when you quantize. And this new sequence is called state variable. Okay, so each element of V collects the error. So for V1, we simply, or for V0, we have the error only from the first two elements of this sequence. And then when we go faster, the larger n is, the more error terms we collect here. Okay, so Vn collects all the error that was made from the step 0 to step n. And we would like to, from sigma delta perspective, we would like to control this accumulated error, and we would like that Q does not approximate Y. We, like element-wise, we say we only would like that this approximation happens in local average sense. Okay, and having these two ideas in mind, the goal is to construct stable quantization schemes. What do I mean by stable? Stable means the following, that if your input signal or your input sequence is bounded, then you can guarantee also that this accumulated error is bounded. And so there exists some gamma such that the infinity norm of the state variable is bounded. Because you wouldn't like that the error explodes, okay? You would like that you accumulate some error, but this error that you accumulate is bounded. It does not explode, because then you might lose the connection between the true samples and the 1-bit samples. That's why the stability idea is very important. And this can be done, this what I mentioned, the controlling the accumulated error, having Q that approximates Y only in average sense, for example, in the following way. So this is the simplest version of sigma delta schemes, which is the first order sigma delta scheme. Why is it called first order? I will explain you in a minute. But let's go through this iterative process. So we have given this sequence of true samples Y, and we would like to replace them by 1-bit samples Q. Okay, so the first order sigma delta scheme tells you the following, that if you are at step 0, so this is where you start, then you simply take the sign of this 0 sample. Okay, so Q0 is simply sign of Y0. And then you collect the accumulated error in the state variable. So you say V0 is the error that I've made exactly at this step. Then in the second step, you take the true sample of the function, and then you add the error that you've made before. And then you take the sign of it. Again, you keep track of the accumulated error. So you say the next element of my state variable is the sum of two errors that I made in these two steps. So you have V0, which is exactly the error from 0 step. And you have now the difference between U1 and Q1. Okay, and you are doing this further. So at in step number Q, you say I take the n sample here, and I add the error that I made in the previous step. And again, you keep track of the accumulated error. And if you look carefully here, you can see that the difference between the true samples and the quantized samples can be represented as backward difference of this sequence Vn of the state variable. And you have here this backward difference of to the power 1. That's why you have here first order. In another way, you can say in each step, I remember only one error that I've made. Okay. Of course, you can ask, can I add here more errors? For example, not only Vn minus 1, but Vn minus 2, or can I remember more? Of course, you can. And in this case, we talk about higher order schemes. For example, for R's order scheme, this sample n, 1-bit sample, is again defined as the taken sign of the true sample. And here you add some weighted average of this state variable. So this H is called the feedback filter, and this H helps you for R's order schemes to collect R terms from the error that you've made. So which means R terms from this state variable. And then the difference between the true samples and the quantized one can be represented in a similar way as before. So for the first order, we have here simply backward difference. For R's order, we need somehow to have connection to the backward differences. And this filter that we use here is defined using R's order backward difference. Okay, so this delta minus H for this feedback filter H should satisfy this condition. So it should be defined as R's order backward difference of some other sequence G. And G can be some, let's say, L1 sequence, okay? So in this case, for R's order schemes, we replace the backward difference by convolution with something that is related to this backward difference of order R. And here is some example. For example, for R1, for first order, you saw already that this thing here is simply delta, which is backward difference operator, or you can represent this as a sequence, so like a sequence from with 1 and minus 1, and all the other elements, they are equal to 0. Then for R equal 2, for the second order, you say here, here's one example. There are many ways to define this, but just to show you something, you can see that there is a way to define such filters. And for 1 decays, this one-dimensional sigma delta quantization is very well understood mathematically. And there are certain points, for example, that are very useful. We have this noise shaping property. By noise here, we mean error, the quantization error. And this noise shaping property tells you that the error signal, this EQ, if you use sigma delta quantization schemes, that this error signal is of high frequency, which means that if the frequency is high enough, then you cannot see any difference between the true signal and the original one. And there is a rigorous performance analysis, for example, from Shannon sampling result, we know that if we have more samples, or if we have higher oversampling rate, that the error or the quantization signal decays with the oversampling. And there are sufficient conditions for stability, which means we know conditions that can guarantee that the state variable is bounded. And this is something very nice. And this is something that we would like to have for digital halftoning, because you can see now clearly connections between digital halftoning schemes and 1-bit quantization. In both cases, we replace the samples by -1 and 1, and we keep track of accumulated error. And once, namely in 1997, there was one conference proceeding with the title Digital Halftoning as Sigma Delta Modulation into D. And what they mentioned in this proceeding, that the digital halftoning schemes must perform the same task as 1-bit sigma delta quantizers, okay? But unfortunately, there was nothing else mentioned about the relation between digital halftoning and sigma delta modulation. Unfortunately for them, luckily for us, because we had an interesting problem to work with. And there are some challenges that are on the way to simply use the one-dimensional sigma delta theory and generalize this to d-dimensional case or two-dimensional case. But for example, one thing that you can certainly do, you can say my image, I can consider this as a 1D sequence if I just glue all the rows together or all the columns, and I can go in this case row by row with my one-dimensional scheme, which means I only add one element from, in this case, from the left to the pixel that I would like to halftone. And this will clearly produce some half-toned image, but you have no, your scheme has no idea that you are living in 2D case. That's why you have here strong artifacts along the lines if you are doing this. Okay, so from visual perspective, it is inefficient because the images, they look very bad. And another way would be to say, okay, we, as you remember, these filters that we had on the previous slide, they were constructed using as backward difference convolved with some sequence. So for the 2D case, you can say I take backward difference in horizontal and vertical direction, and I convolve both of them, which will produce some feedback filter for sigma delta quantizer, and you can quickly generalize the theory behind. But the problem is that even for this case, when we have here two simple schemes of first order, when we take here backward difference of first order and here backward difference of first order, we cannot guarantee that this state variable is not exploding, because this filter that you get, this H, has the L1 norm that is bigger than 3. And here you can see how this filter looks like. So you have 1, -1, and 1. And we cannot guarantee stability for such filters. Interestingly enough, recently it was shown that such filters, they do enjoy stability, but in case when you increase your alphabet. So you are not in 1-bit case, when you have only 2 elements, you are in the 2-bit case, okay? And for 2-bit, you can get stability. But our idea was to use this for digital halftoning, where you have only 1-bit alphabet. That's why we had to do something else. And here, before I introduce to you what we propose, we need to fix some notation. So in the 2D case, what you can do, surely, if you have some direction D and you have some sequence, let's say the state variable in 2D, and you have one-dimensional filter, to somehow marry these two guys, what you can do, you can simply cut your 2D sequence or image in this direction D, which produces 1D sequence, and then you can do all the stuff that you were able to do in one-dimensional case. Okay, so in this case we define two concepts that we not define them, but we use them. They were already defined a long time ago. So we have this directional finite difference, which tells you that if you have 2D sequence and direction D, you cut at some, you cut this sequence in this direction, and you compute the backward difference of order R in this direction. And the same way, if you would like to have this directional convolution, so you cut your 2D sequence in this direction and you convolve this cutted sequence with 1D filter in the usual way. Okay, so you have 2D picture, you cut this in one direction, and then you do your usual job as in 1D for this particular directions. Okay. Good. And here is the definition of weighted quantization scheme. So we say the following. We fix some set of directions, Dij. So for example, here in this figure, you have this set of directions that are denoted by red arrows. And for each direction, you have the corresponding weight, which we call now by W. And all these weights, they are collected in some big matrix, which is called weight matrix. And the sum of the elements of this weight matrix is equal to 1. And all of them, they are strictly bigger than 0 or 0. So I would say they are non-negative. Let's put this in this way. Okay. And what we propose is the following. If you have a 2D sequence of samples of some band-limited function, then to use first order weighted sigma delta modulator or quantizer that corresponds to this weight matrix and to the set of directions, you do the following. To have to replace in step n the true sample yn by its 1-bit sample, you compute this directional backward difference in each direction. You weight them correspondingly with the way with the weights that are dictated by this weight matrix, and this what you are doing is for the state variable. So you collect the errors that are defined by the state variable in different directions. Okay, you by computing this backward difference, and then you weight them correspondingly using these weights. You sum up all this together, and then you add now this one true sample, and then you take the sign. And in this case, the difference between the true samples and the quantized one is written as weighted average of different backward differences in different direction. Okay. And what we were able to show is the following, that if you have some function that is band limited and you have a lattice that is dense enough to identify this function uniquely, and you construct this 1-bit sample Q, 1-bit samples Q using the scheme that I just showed to you, then it defines this quantized representative FQ such that if you measure the error between the signal and this quantized representative, then this error decays with the oversampling rate, with lambda, okay? And here you have the infinity norm of state variable. So you see here we need for sure to have state variable bounded, because if the infinity norm explodes, then this bound has no meaning at all. And then further you have something that depends on the gradient of the kernel that you use for Shannon sampling theorem. You have here some term that is of order 1 over lambda again. And you have some constant CW. And this CW depends on the weights that you have for your first order sigma delta quantization scheme. So this constant looks ugly and is not so compactly represented. But what you can see from here, if this constant can be made small, then you can improve on the error decay, which means if this guy here is very small, this second guy here decays like 1 over lambda, which means if CW would be small, then the error in general would be smaller. And this is something that we really see in the experiments. I will show this to you, but up to now you can see the result. Okay, so you see that if you use first order sigma delta weighted sigma delta scheme, then this error decays like 1 over lambda to the power of this order of the sigma delta scheme. Okay, and here you can see some examples of this weighted sigma delta schemes. For example, the simplest one would be to take 2 directions, the horizontal one and the vertical one, and you weight them with 1/2. So we have this weight matrix. And for this weight matrix, you have the following constant, this constant that I just showed to you, this CW. For this case, it is equal 0.7. Okay, so now if you look for at the Floyd-Steinberg scheme, then again, this Floyd-Steinberg scheme that was not having any theory or explanation. Now we can interpret the scheme as one of the weighted sigma delta schemes. And for this scheme, you have constant C that is 0.64. And we were wondering how small this constant can actually be made. And the good news is that you can make this constant as small as you wish. And for example, there is this minimal constant scheme, which tells you that if you have this weight matrix W, then what you need to do, I explain you here on this picture. You need to set only 2 weights that are non-zero, and all the others, they should be set to 0. So the one is that just standing here near the point when you would like to halftone your picture. And another one, this S here indicates the position of this column. Okay, so the larger S is, the more you need to push this W to the right. And what this minimal constant scheme tells you, that to have this constant C very small, you need to enlarge this S, which means you need to push this element here very far away to have an infinity norm that is small. And first of all, we thought, okay, it cannot be like this because it is completely counterintuitive. This means that this guy here needs to be pushed far, far away. But we do see this in the numerical experiments for infinity error. But this is something that we still do not understand why it works like this. Okay, this was about first order schemes. And now if we go to higher order, then we can have something similar as we have done before. So we again have some weight matrix W, okay, with again the sum of its elements equal to 1, and all the elements, they are non-negative. And then you again fix some set of directions, and in each direction you cut your image, you get 1D sequence, and you convolve the sequence with the corresponding feedback filter with H. Okay, you have this different filters for different directions. You convolve in different directions for your state variable. You collect the error you have done before by computing this convolutions, and then to compute the 1-bit sample from your initial sample, what you do, you sum up all the directional convolutions that were computed with this feedback filters and the state variable, okay? And then here again, you can represent this difference between the true signal or the true samples and the quantized one using this representation when we have directional convolutions. These formulas, they look like crocodiles. I can understand this completely, but once you've done this for one or two feedback filters here, okay, then you can understand what is going on, okay? So the general idea is that you fix some directions, and in these directions you compute convolution, directional convolution with the state variable and the corresponding feedback filters. And these feedback filters, you can choose whatever you want to, but they need to satisfy this backward difference definition. And then you collect the error, you add this error to the true sample, and you quantize, and you keep track of the accumulated error. And of course, here, this order of the scheme is dictated, as in the one-dimensional case, by definition of this delta minus hij. And when order is R, then we can also have some guarantees for error decay, namely, we have the following. So again, you have a band-limited function and a lattice that uniquely defines this function. And if you construct this one-bit sequence using R's order weighted sigma delta modulation scheme, the one that I presented to you just before, then you know that the error between the quantized representative and the function decays like 1 over lambda to the order of the scheme. Okay, so here you see for when R was 1, we had here only 1 over lambda, and when R is as some general number, let's say 2, then you would have here like 1 over lambda squared. And again, here we have some constant that depends on the weights and on the order of the scheme. And we have some other terms that decay with with lambda. Okay, this is about error bounds, but I mentioned to you that stability is very important in this case. So here we can also guarantee stability in the following case. If we have that all these feedback filters, they have the one norm smaller than 2, then we can guarantee that state variable is uniformly bounded. In particular, if this equality here is satisfied, so the weighted average of L1 norms of H plus the amplitude of the signal is smaller or equal than 2, then we know that the state variable is smaller than 1. Okay, and now we go to numerics. Here you can see some band-limited function, and it's an approximation with some oversampling rate lambda. So the approximation error is 10 to the power minus 3. And here you can see the plots of quantization error of this error signal, okay? So here is the case when we have only quantization row by row for this 2D function, and you see that this quantization error is especially big in this case when function is changing a lot. Now this quantization error is corresponding to this simple average scheme when you take the horizontal and the vertical direction and you average with weights 1/2. So you see the error is now in the infinity norm smaller than the one for row by row, but it is distributed overall. So you have an error overall, but it is not very big. And here is an example of choosing one of the optimal schemes, one that I showed to you with minimal constant scheme. So in this case, we've chosen the matrix of size 4, and you see that this optimal schemes, I would say, for the infinity error really do the job, because the error is everywhere smaller than for those two schemes. And for some other optimal schemes, we can also see the decay of the error. Okay, but the initial the initial motivation was to use this weighted sigma delta schemes for image halftoning. So here is an algorithm how you can do this. Of course, you can do this not only for grayscale images, but for RGB images. And then in this case, you consider you consider each matrix of red, green, and blue as one separate matrix, and you apply this quantization schemes for each of the matrix, which means you have this RGB image, which can be represented as a matrix. You convert this to double, and then you have here some sharpening, I would say initialization. What we notice that the images, if you do not do this sharpening, which means you simply increase the colors by a bit, then if you don't do this, that images look very faded. Okay, that's why we came to this idea to elevate the colors a bit. And then you have this weight matrix, you have feedback filters that you use, and you have here some stability constant for second order schemes. So for second order schemes, we cannot take the amplitude one, we need to take this one, which you cannot notice for images, but it is visible for numeric. Okay, and then for each of your colors, R, G, and B, and for the size of the image, you run this quantization scheme for corresponding weights and filters, and then you get 1-bit image. You, for example, save this as BMP, and then for halftoning, we used here not the infinity error as for functions, but we used the feature similarity indices to compare two images. And what is this feature similarity index? Feature similarity index is one of the indices that is related to image quality assessment, and it does the following. So you have two images. The one is the original one, and the second one is the one that is perturbed. So you have some noise. And for halftoning, we can interpret the halftoned images as the one that are that have some noise on it, or that are somehow disturbed. Okay, and then for the true image and for this one, for the one with noise, you have the following decomposition, which is called YIQ. So basically what you do with your image, you decompose this image into 3 elements. The one that is simply grayscale image, and the 2 that correspond for the colorful part of the image. So this is achromatic part and this is chromatic part of the image, and you compare the gradients with some particular functions. And the idea is that these images, these indices for images, they can have they can reach 1 in case when 2 images are identical. Okay, so if 2 images are identical, you have 1, and the more noise you have on your image, or the smaller this index is, and the lowest value it can have is bounded from below by 0. For example, if you have 2 different images, then the index is like 0.2 or 0.3, so it does not really go to 0. But we use the similarity indices as they are state-of-the-art indices for comparing 2 images, the original one and the one that is corrupted by noise. And what we have got is the following. So here you can see this feature similarity indices for grayscale images and for RGB images. And we tested here different halftoning schemes that were already some way around, and the one that we propose with weighted sigma delta schemes. So here you can see that the higher the index is, the better this scheme works. And this is average over 50 images. So for each method, we have the original image and the one that we half-toned with the particular method here, and then we average over 50 images. And here you see that the lowest similarity index is both for RGB and for grayscale is the case when you use this 1D scheme, going row by row. As I mentioned to you, it is doing very bad for your image. And then this schemes here, this is some scheme from digital halftoning from engineering literature. This is the Steinberg-Floyd method, or Floyd-Steinberg, the one that I showed to you. And this is optimal 4. The optimal 4 is the one that was very good for infinity error. And now you see that both for grayscale and for RGB, this opt4 is not giving the best result. And of course, we understand this because we use this infinity error to design weighted sigma delta schemes, but using the infinity error to measure similarity between the index between the images is not the best way. Okay, you can have on one pixel that infinity error is very big, but the image in total can be very good, so your eye will not notice it. That's why we understand that this opt4 methods, they work very good for functions, but not so good for images, although they are doing better job than only going line by line. But interestingly enough, we can see that second order schemes, they are doing the best job in both cases, for RGB images and for grayscale images. And even though they were not designed to optimize this feature similarity indices, but they are good both for infinity error and for similarity indices. And here is some example. You can see that this is the original image, so of this size, and you can see some particular parts that are enlarged of this image. Here on the right-hand side, you can see half-toned image, the one here that is half-toned. So we replace only by white or green, white or red, or white or blue. And you can see that the similarity index between this image and the original one is 0.93. And here is another image, which is also a half-toned version of the original one. And for this image, the similarity index is higher. And to construct this image, we used the second order weighted sigma delta scheme. And you probably could also see that the dots here, they have a bit better patterns than here. Here you can see more artifacts, which is representing one of the figures that I just showed to you that we used for numerical experiments. Okay, and about future work and launched projects, what would be interesting to investigate in this direction. So we would also be interested in using dynamic filters, which means here we have one filter for the complete image. Maybe one can divide image into sub-images, and then for each sub-image one can use different filters. Maybe it would lead to a better performance. What would be also interesting is to have weighted sigma delta schemes on manifolds. This is something that we started working on, but there is still a lot of job to do, and of course quantization on graphs. So these are the problems that I think are very interested to investigate in future. And here, if you are interested in this topic, then here is some articles that you can look at. And at this point, I would like to thank you for your attention.
Thank you, Hannah, for the nice talk. I have one question. It's maybe very high level. but this finite difference operator,
Yes.
that makes one think about differential equations, of course. So my question is there some differential equation interpretation of this method?
Yes, I think that there are some results that investigate stability from perspective of differential equations. Yes, so I know what you mean. I worked a bit with finite difference method, and there are of course different backward differences that you can use, right? And the question is, would they lead to a better result or not? I do not know any result that is going on in direction of error decay from the perspective of differential equation, but I do know that there are some results about stability that interpret this sigma delta schemes as dynamic, some dynamic equations, right?
Cool, thank you.
Can I maybe compensate with a very low level question? Which, I mean, you have these matrices, and then you're quantizing with the surrounding neighbors. What do you do at the border?
Yes.
Do you wrap around or do you cut off?
For this experiment, we cut off, but you can also interpret images as something that is on the torus, right? And now we started working on this manifold business with torus. And of course, we have problems because on the boundaries, we have strong artifacts. So if you glue them together, then you have some artifacts. And this is something that we try now to work on and to have better results for the boundary, because of course initially when you start halftoning, then you have no error that you remember. That's why the quantization is not or halftoning is not working very well, and then the more you go in your image, the better it works. So you can also say I just initialize randomly my state variable for the points that I have no information at all. It helps a bit, but it is not I think that there is something that can be done more efficiently than just saying I have some normal distribution evaluation for the points that I haven't seen before. Yeah.
Yeah. So could you imagine other directions, just like a spiral?
Yes.
Or is it always the beginning that is the worst?
I haven't tried with spiral, but what I tried is going zigzagging.
Yeah, that's also nice.
And I didn't see much difference in the similarity indices, to be honest. So
you have to pick the corner which is going to be worst. Basically.
Yes, probably. I need to have a more sophisticated way of choosing where do I start, because now for this experiment, what we've done, we start only on the top left corner, and then we go row by row. You can also start here and go like zigzagging, but between these two things, I haven't seen much difference in the similarity indices business and for visual performance also. So.
So then I think it was a really lovely talk. Thank you so much. I hope it will attract the audience that it clearly deserves on YouTube. Because me not understanding anything about sigma delta quantization before, I was very, very, very happy. Thank you very much.
Thank you very much for such a wonderful feedback. I'm very glad that